Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I was to tell about the numerical problems on optical fibers or numerical problems on fiber optics. So, the first problem is a step index optical fiber has a numerical aperture of 0.16 and core refractive index of 1.45. Estimate the acceptance angle of the optical fiber and refractive index of the cladding. So here, a step index optical fiber has numerical aperture and the numerical aperture value have been given, and a core refractive index of optical fiber is 1.45, and have to calculate the acceptance angle of the optical fiber and refractive index of cladding. So let's see what are the data have been given. So let's solve the problem. So the data given is numerical aperture. The numerical aperture value is 0.16. 0.16 numerical aperture 0.16, and then core refractive index. Core refractive index usually N1, so N1 is equals to 1.45. But what we have to find? We have to find the acceptance angle I maximum and then refractive index of cladding. So both we have to calculate. So usually the optical fiber construction already we have seen. The inner layer is core having refractive index N1. Surrounding core there is an outer layer which is cladding. And right here. So outer layer is cladding. And this is fiber axis. So core refractive index is N1. So N1 is equals to 1.45. And cladding refractive index we have to find. And numerical aperture value also given. So the numerical aperture is the capacity of light gap of a material. So numerical aperture is the light gathering ability of a material. So the light gathering ability of a optical fiber. So 0.16. Have to find N2, that is cladding refractive index, and I maximum, that is acceptance angle. Acceptance angle is the maximum angle that enters into the core with the fiber axis. So So the maximum angle with the fiber axis that enter into the core. So this is the core, this is the instant light. So the light is entering from the air medium into the core with some angle, maximum angle with the fiber axis. So this maximum angle we are going to determine. Okay, so we have to find cladding refractive index N2 and the maximum angle of light that enters into the core. So these two values we have to find. Okay, so numerical aperture NA is equals to 0.16, refractive index of core N1 is equals to 1.45. So we have to find acceptance angle and then refractive index of cladding. So what is the formula? So the formula for acceptance angle is sine inverse of NA. Sine inverse of NA. So sine inverse of NA, where here sine inverse of NA already NA value have been given. So sine inverse of numerical aperture value is 0.16. So sine inverse of 0.16 we have 9.206 degrees. So this value is, so the angle with the fiber axis is 9.206 degrees. With this maximum angle with fiber axis, the light is entering into the core. So acceptance angle is 9.206 degrees. And to find the refractive index of cladding. So to find the refractive index of the cladding, we have to take the N2 from the formula. NA is equals to root of N1 square minus N2 square. N1 square minus N2 square. So here, this is the numerical aperture formula. From this formula, we are going to take it out N2. So when doing this one, we'll get NA square 2. Root of N1 square to N2 square. So here, NA square so this implies when taking this into, it is equals to N1 square minus NA square. So from this, we took the refractive index of cladding N2. N2 is equals to root of N1 square minus NA square. So let's substituting the values of N1 and then NA. So we know that this is the N1 value for refractive index 1.45. This is numerical aperture 0.16. So root of N1 square minus NA square is equals to root of 1.45 square minus 0.16 square. So the value of 1.45 square is 2.1025 minus 0.16 square is equals to 0.026. So root of 2.1025 minus 0.026. So the value is 1.44. So this is the refractive index of cladding. So this value is I maximum. So I maximum is equals to 9.206 degrees. So for refractive index, and this cladding refractive index is how much value we got? N2 is equals to 1.4. So we found this two. Okay. So we shall move to the next problem. The refractive indices of core and cladding materials of a step index optical fiber are 1.48 and 1.45 respectively. So estimate numerical aperture result. Calculate numerical aperture and then acceptance angle. So the data given in a problem is refractive index of 4. So 4 refractive index is 1.48. And y is equals to 1.4. Cladding refractive index N2 is equals to 1.45. So wanted to calculate NA, numerical aperture, light gathering ability of the optical fiber, and then I maximum, that is acceptance angle. So the angle made with fiber axis to enter into the core. So this is the incident light ray. So this is I maximum. So this we need to find. Okay. So to find the numerical aperture, we have the formula. So the formula which we are using, numerical aperture NA is equals to root of N1 square minus N2 square. And so N1 and N2 is given. So that root of 1.48 square minus 1.45 square, that is equals to 0.2965. So this is the numerical aperture value. In coming to the calculation of acceptance angle, I maximum. So I maximum is equals to sine inverse of NA. So sine inverse of NA, as we calculated sine numerical aperture NA is 0.2965. Let's substitute here sine inverse of 0.2965. So we got the value 17 degrees 15 minutes. So this is the acceptance angle. That is, this angle is 17 degrees 15 minutes. Next problem. An optical fiber has a numerical aperture of 0.2 and a cladding refractive index of 1.59. Find the acceptance angle for the optical fiber in water, which has a refractive index of 1.33. So the data numerical aperture is given 0.2, cladding refractive index N2, refractive index of cladding is N2 1.59, and then Refractive index of water N naught 1.3. We need to find acceptance angle I maximum. I maximum. This we need to find. So, what are the formula we are using here? First, I maximum. The formula for I maximum acceptance angle is equals to sine inverse of NA. Here, sine inverse of NA. So, here NA is equals to root of N1 square minus N2 square by N0. So, when there is a refractive index of current cladding, we usually take NA is equals to root of N1 square minus N2 square. But when there is a different medium, we are using by N0. Why? Because usually NA is equals to root of N1 square minus N2 square by N0. So, where N0 value for air medium N0 is equals to 1. So NA is equals to root of N1 square minus N2 square by 1. So the numerical aperture will be N1 square minus N2 square. So that's why we do like this. Okay, where in this case the acceptance angle for the optical fiber in water which have refractive index. So instead of N0, we have to take 1.3. Okay. So that's why when for the air medium we are taking N0 is equals to 1. That's why NA is equals to root of N1 square minus N2 square. We are using the formulas in some of the problems where there is a specific medium have been given. So with current cladding, then we use the formula NA is equals to root of N1 square minus N2 square by N0. Okay. So here I maximum is equals to sine inverse of NA. Okay. So NA is equals to root of N1 square minus N2 square. This is for current cladding. And repeat current cladding. So when we take a N0, so when we take N0, that is a refracting index of other medium, then we use this one. Let here NA is given 0.2. That's why NA is equals to root of N1 square minus N2 square is equals to 0.2. Okay. So we're calculating I maximum sine inverse of NA. So this NA is sine inverse of numerical aperture, which we are using this formula N1 square minus N2 square by N0. Because find the acceptance angle for the fiber in water. So that sine inverse of 0.2 divided by 1.33. This is a refractive index of the water. So calculating this formula, simplifying this, we get a sine inverse of 0.1504. Sine inverse of 0.1504 will get 8.6487. This is the I maximum. So the optical fiber is in water. So here So core, cladding, and this refractive index is N1, this refractive index is N2. This refractive index is N1. So light is entering with maximum angle in fiber axis. So incident light ray. So here it is I maximum wanted to find. So here the refractive index is N naught. So N naught, that is what? So the optical fiber is in water. So this optical fiber is in water, placed in water, so that from the water the light is entering into the optical fiber, so that the refractive index of the water is A naught, that is equals to 1.33. Okay, so in this case we found that I maximum. Okay, so that's why we use a I maximum is equals to sine inverse NA, where NA here root of N1 square minus N naught, N1 square minus N2 square by N naught. So this value have been given in the formula, that is 0.2. So 0.2 by water refractive index is 1.33. Okay, so simplifying this, the I maximum acceptance angle, maximum acceptance angle is 8.6487 degrees. Is calculate the refractional index change. Calculate the fractional index change for a given optical fiber. For a given optical fiber, if the refractive indices of the core and cladding are 1.563 and 1.498 respectively. So the data given here, refractive index of core N1 is equals to 1.563 and refractive index of cladding N2 is equal to 1.498. So we have to find the fractional index change. Fractional index change delta we have to find. So formula of fractional index change delta is equals to N1 minus N2 by N0. So N1, N2 have been given. So here N1. So fractional index change delta is equals to N1 minus N2 by N1. So this is the formula. So let's substitute the N1 and N2 values. So delta is equals to N1 minus N2 by N1. So N1 is 1.563 minus N2 is 1.498 divided by 1.563. Okay, so minusing 1.498 from 1.563, we get 0.065 divided by 1.563. So the value of this is 0.0416. This is the fractional index change. Fractional index change of core and cladding. So delta is equals to N1 minus N2 by N1. So the value is 0.0416. So next problem. When the mean optical power launched into 8 kilometer length of optical fiber is 120 microwatts. 120 microwatts. The mean optical power at the fiber output is 3 microwatts. 3 microwatts. So find overall signal attenuation and signal attenuation per kilometer. So overall signal attenuation and then signal attenuation per kilometer. So both we need to calculate. So the data what they have given here. So length of the fiber and then input input power of the optical fiber and then output power of the optical. So here the data to solve the problem. First we shall write the given data. So length of the optical fiber capital L is equals to 8 kilometers. Optical fiber length is 8 kilometers. So input power, the input power of optical mean optical power of optical fiber Pi is equals to 120 microwatts. So the input optical power Pi is equals to 120 microwatts and mean optical output power P naught is equal to 3 microwatts. So 3 microwatts. So we have to find the overall signal attenuation. To find overall signal attenuation and then signal attenuation per kilometer. These two we have to find. Okay, so first we shall calculate the overall signal attenuation or loss in decibels through the optical fiber. So that is signal attenuation or for decibels length is equals to 10 log 10 of Pi by P naught. That is 10 log of Pi by P naught base 10. So the Pi is, so as Pi is 120 microwatts, P naught is P output is, that is Pi is input power. Input power Pi is equals to 120 microwatts and output power P out is equals to 3 microwatts. Okay, so let's substitute 10 log of 120 into, as it is in microwatts, I have to change it watts. So 120 into 10 power minus 6 watts. So here also 3 into 10 power minus 6 watts. So that minus 6 divided by 3 into 10 power minus 6. So it is equals to 10 log of. So cancel. So 40. So 40 is 10. So the value of this one is 16.0 decibels. So signal attenuation is equals to 60 decibels. And the next one is signal attenuation per kilometer for the optical fiber. So alpha decibels L is equals to 16.0 decibels. So as we have to take 8 kilometers, L is equals to 8 kilometers. So that we have to calculate per kilometer. We have to calculate per kilometer. So that alpha, so signal attenuation that is equals to 16.0. That is here signal attenuation is equals to 16.0 decibels. Thus, we need to calculate per kilometer. So, signal attenuation per kilometer for dB is equals to 16.0 by capital L decibels per kilometer. So, alpha dB is equals to 16.0 divided by per kilometer means 8 kilometers for 8 kilometers because the L length of the fiber is 8 kilometers. So that 2.0 decibels per kilometer. So overall signal attenuation is alpha dB. L is equals to 60.0 decibels. This is overall signal attenuation. Where signal attenuation per kilometer. So we'll get alpha dB is equals to 2.0 decibels per kilometer. So this we go. Okay. Now these are the problems which are related to the optical fibers. So in the next session we shall go for the another module which is magnetism, which is of the magnetism of the superconductors. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.